Have you ever wondered if there's a speed limit for computing? You know, a point where no matter how clever you get, an algorithm just can't go any faster? Well, today we're diving deep into one of the most fundamental problems in computer science, sorting, to find out. So, you've probably heard of the classics, right? Merge sort, heap sort, quick sort, they're all fantastic, but they have this really weird thing in common. They all seem to max out at the same speed, what we call n log n time. Basically, that means if you double the stuff you're sorting, it takes a little more than double the time, which is super efficient, but not perfect. And the big question is, why? Is this just some cosmic coincidence, or have they all slammed into some kind of invisible wall? The secret that ties all of these algorithms together isn't some crazy complex formula. Nope. The answer is actually hiding in the very simple strategy they all use to get the job done. They're all what's known as a comparison sort. So what does that actually mean? Well, a comparison sort works pretty much the same way you or I would sort a deck of cards. It picks up two elements at a time and asks a super simple question. Is this one bigger than that one? That's it. Algorithms like insertion sort or merge sort, they rely entirely on these less than or greater than questions to figure out where every single thing is supposed to go.
But here's the catch. As simple as that strategy is, all of those questions create a fundamental limit. It leads us straight into what I like to call the comparison trap, and it explains exactly why that speed limit we talked about even exists.
To really get the trap, you have to appreciate the sheer scale of the problem. If you have a list of n items, there aren't just a few ways they could be scrambled. There are n factorial possible arrangements. Let that sink in. For just 10 items, that's over 3.6 million possibilities. The algorithm's job is to find the one single correct order out of all those millions. We can actually draw this out using something called a decision tree, just like the one you see here. Think of it like a game of 20 questions. Every comparison the algorithm makes, like is A bigger than B, is a fork in the road. This creates this huge branching tree. The algorithm just follows a path down, making one decision at a time until it hits a leaf at the very bottom. And each leaf represents one of those unique sorted outcomes. So here's the kicker. For an algorithm to even have a chance of being right, its decision tree has to have enough leaves at the bottom for every single one of those n possible ways the input could have been arranged. And since each comparison only gives a yes or no answer, which is basically just one bit of information, we have to ask enough questions to tell all n factorial of those outcomes apart. And this is where it all comes together. It's actually a pretty elegant proof. You start with n factorial possibilities. Each question you ask, at best, cuts the number of remaining possibilities in half. So the minimum number of questions you have to ask is the height of this tree, which, mathematically, has to be at least the logarithm of n factorial. And through a little bit of math magic, the logarithm of n factorial just happens to be pretty much proportional to n log n. And that's it. That's the unbreakable speed limit. Any sort that relies on comparisons must take at least n log n time in its worst case. Okay, so if the whole speed limit is caused by comparing elements, what if we just stopped comparing them? This brings us to a really clever cheat code of an algorithm, one that just breaks the rules and smashes right through that n log n barrier. Let me introduce you to counting sort. Counting sort completely sidesteps the comparison trap by taking a totally different approach. Instead of asking which element is bigger, it just uses the actual values of the elements themselves to figure out where they belong. Let's look at them side by side. Comparison sorts ask these relative questions, right? That makes them super flexible. You can sort numbers, letters, you name it. But they're stuck with that n log n speed limit. Counting sort, on the other hand, asks an absolute question. How many 3s are in this list? How many 5s? Now, this only works for integers in a specific range, but look at that speed, n plus k, which can be way, way faster. Let's trace how this thing actually works. First, you see that array C? The algorithm just zips through the input and counts how many times it sees each number. So in this example, it found 2 zeros, 2 2s, and 3 3s. Simple enough. Then it uses those counts to figure out the final position for each number. And from there, it can build this sorted array B directly, just plopping every element into its correct spot without a single comparison. It's honestly more like organizing than sorting. Of course, there's always a catch, right? This amazing speed comes with some major strings attached. Counting sort is definitely not a silver bullet. It only works if your data is integers and you know the maximum value, what we're calling k. If that range K is massive, like imagine your list has 10 numbers, but one of them is a billion, the memory and time it needs just explodes, making it way slower than a simple comparison sort. And this teaches us something really important. The best algorithm always depends on the specific problem you're trying to solve. This whole discussion about speed limits and best cases brings us to the formal language that computer scientists use to talk about all this stuff. To really understand performance, you've got to learn to speak the language of asymptotic notations. There are three big ones you'll see all the time. There's big O, which you've probably heard of. That represents the upper bound, the absolute worst-case scenario. Then there's big omega, which is the lower bound, or the best case. And finally, big theta, which gives you a tight bound, basically the realistic average case. Let's start with big O. This is the most common one because it gives you a guarantee. When we say an algorithm is O of n squared, what we're really saying is that its performance will never get worse than that. For really critical things like, say, an air traffic control system, you don't care what the average speed is. You need to know the absolute worst it can possibly be to guarantee it's safe and reliable. Next up is big omega. This is the other side of the coin. It tells you the absolute fastest an algorithm can possibly run. Remember when we proved that comparison sorts are omega of n log n? We were setting a floor. We proved that no matter how genius your algorithm is, it can never, ever be faster than n log n in the worst case. That is the fundamental speed limit we've been talking about. And finally, we have theta. You use theta when an algorithm's best and worst case performance are pretty close to each other. It gives you a really tight, precise picture of how it usually behaves. When we say counting sort is theta of n plus k, we're giving a very accurate description of how it will perform, because its runtime doesn't really have these wild swings. So from sorting speed limits all the way to the language of efficiency, it really all comes down to trade-offs. The fastest algorithm isn't always the most flexible one. And that leaves us with one last thought. Every single piece of software you use is built on these kinds of decisions. So the next time you use an app, ask yourself, was it designed to be fast most of the time? Or was it built to be rock solid even in the absolute worst case scenario? The answer tells you everything. Thanks for joining me on this deep dive.